Okay, so I think we are live now. Let me share my screen. Can someone confirm that you can that the screen is visible?
Yes, sir.
Okay, thank you. Okay, so good afternoon. So this is our 9th lecture on cryptography. So you might be thinking what we are doing till now. As you know that we have covered certain basic classical crypto systems, like certain basic ciphers, and we have done the cryptanalysis for them. After that, we were developing some probabilistic ideas, and especially perfect secrecy ideas of Shannon, right? And we talked about entropy of a random variable. So we defined random variable. So what is a random variable? Random variable x bar consisting of two things: a finite set x and a probability distribution associated with x, right? So then we talked about entropy of a random variable. So these concepts are pretty important because your plain text, ciphertext, and key, each of the three things you can visualize them as a random variable. So basically you can talk about the entropy of these things, and this entropy is pretty useful. So today is the last class in terms of background, and towards the end of the lecture I'm going to give you some ideas about the projects, because projects are important in this course. As you know, there is no final exam, only project we are thinking right now. There is only one exam in between, so basically you have enough time to do some interesting project, so we'll talk about more about it later on, but anyway, so that is the key idea. So I hope by the so after today, in the next class we will focus on specific crypto systems like DES, digital encryption standards, and advanced encryption standards, AES. Those are two popular crypto systems widely used. So I'll talk about it. And these ideas about the probability, entropy, these things are pretty useful to do the analysis of the crypto systems, so that we understand really well. Okay. And okay, so that is the thing. So let me see what we have covered till now. I'll just show you in the slides. So we talked about discrete random variable x, it's a finite set. And let me choose the pen here. Yeah. So we talked about this discrete random variable consisting of finite set x and a probability distribution of x, right? Then we talked about joint probability and conditional probability. So this joint probability and conditional probability, right? Then random independent variables. So independent random variables. When joint probability is product of the two probabilities. Then we, using the techniques of Bayes' theorem, we obtained many things. Then we discuss perfect secrecy. Okay, so a crypto system is said to be perfectly secure provided we have this condition: the probability of x condition y is same thing as probability of x for every x in plain text and y in ciphertext. Okay, and we have shown to you that shift cipher is perfectly secure. Then actually we talked about certain more characterizations, especially yeah, so we talked about entropy of a random variable. So if x bar is a random variable, what is the meaning of entropy of a random variable, right? And so here it is defined: if x bar is a random variable, hx bar is equal to minus summation x in x probability of x times log 2 base probability of x, right? This is the definition of entropy of a random variable. After that, we actually derived some formulas for properties of entropies. Of course, now since k bar is a random variable related to key, P bar is a random variable related to plain text, C bar is a random variable related to ciphertext. So we can compute the entropy of each of these things, right? This is something pretty common, and I have given you an example for that. Okay. Then using strictly concave function or concave function, and we using Jensen's inequality, we did some calculations, right? So we talked about, so we last time we shown to you this theorem that hx comma y less than or equal to hx plus hy, right? So entropy of x joint y is less than or equal to entropy of x plus entropy of y, with equality if and only if x and y are independent random variables. Okay. So today actually, after that we can talk about conditional entropy. I think you remember the proof. It's not very difficult. Here we applied Jensen's inequality, okay, at this place, and then we arrived at the proof, right? So basically, that's all. So today I am going to talk about conditional entropy. So we are about to finish this basic stuff. Then the course is really fun after that, But these things are pretty important for you to understand. So suppose x bar and y bar are random variables, discrete random variables, what I mean. Okay. Then for any fixed value y of y bar, fixed y of y bar, we get a conditional probability distribution on x, and corresponding random variable we denoted by x bar comma y. This is the corresponding random variable that we denote. Conditional probability distribution of x, right? So we have, I call it as h x y summation x over x probability of x condition y log of 2 base probability of x condition y. That's a pretty basic thing, right? So using this idea, we can define what is known as conditional entropy. Okay, so conditional entropy, we denote it by h x bar y bar. Okay, so h x bar pipe y bar is equal to minus summation over y summation over x. This is double summation probability of y probability of x condition y. You can see difference log 2 base x condition y. Okay, so this is nothing but a weighted average with respect to the probability. This is weighted average with respect to probability of y. Okay, this is a weighted average. Okay, so this measures the average amount of info about x that is not related to y. Okay, so this is how we compute conditional entropy. So now I think there are two more results which I would like to mention here. Without proof, of course, hxy bar is equal to hy bar plus h bar y bar. Okay, so joint entropy of joint random variables is like this plus conditional entropy actually. This is one result. Another result is kind of corollary of this result, that hx y conditional entropy cannot exceed h of x bar with equality if and only if x and y are independent random variables. Again, I am not giving any proof of this fact, but this is just a corollary to this. Okay. Now, in terms of random variables, like for the key and the cipher text, we can actually compute the conditional entropy, HKC. Okay. So this measures the amount of uncertainty of the key remaining when the cipher text is known. Okay, so this is a important parameter. Okay, entropy of conditional entropy of K and C. In fact, we have a formula, in fact, a theorem which I can mention, and I can give you a quick proof of this fact. So HKC here. Remember, K is a random variable corresponding to key, and C bar is a random variable corresponding to cipher text. So if we have P, sorry, I should write it down. If you have P, C, K, E, D, this is our crypto system. Okay, and so K bar and C bar are the random variables corresponding to key and the cipher text. Then this is equal to H of K plus H of P minus H of C. Okay, so entropy of key plus entropy of plain text minus entropy of the cipher text. This is the conditional probability. So conditional entropy. So here is a small nice proof. Some of these things I will quickly give you. Observe that HKPC is same thing as HCKP plus HKP. Okay. Now the key and the plain text determine the cipher text only. Key and plain text determine the cipher text, right? That means we have this condition here only. Why? Because y is equal to ek of x. Cipher text is related to plain text via these encryption. This implies that we have h c k comma p is equal to 0. So this quantity will become 0 here. So we have h k p c entropy is equal to hk h k p. But this quantity is nothing but is equal to hk plus hp. Why? Because k and p are independent random variables. Are independent random variables. So this sum is equal to this quantity, right? So basically HKPC is equal to, I can say that HKPC is equal to this quantity, right? This is one thing. Also, since the key and the ciphertext determine the plain text only, that is x equal to dky, we have another result. Since x is equal to dky, when ciphertext is given, we can find out the plain text. Okay, so that means we have h P K comma C equal to 0, 5. So H K comma P comma C will also be equal to HKC. We can do the similar thing again, right? This implies that by comparing this and the previous result, we have H K C is equal to HKC minus HC. Okay, from the previous result here. So this HKC is equal to HKPC minus HC. Now this is nothing but HK plus HP, entropy of P minus entropy of C. So this is a simple result. Okay. In fact, I can give you a quick example here so that we know what is happening here. So earlier we have determined that HP is equal to 0.81 in the previous examples we have done in the last class, actually equal to 1.5, and HC is equal to 1.85. So using this theorem, HKC is equal to 1.5 plus 0.81 minus 1.85, which is equivalent to 0.46. Entropy, this conditional entropy is this thing. Okay. In fact, we can verify this. So essentially, directly if we compute probability of K bar is equal to Ki, condition Y is equal to J, 1 less than equal to I less than equal to 3, 1 less than equal to J less than equal to 4. This is from the previous example, So we can compute 1 probability of K21 is equal to 0, probability of K31 is equal to 0, probability of K12 is equal to 6 by 7, probability of K22 is equal to 1 by 7, probability of K32 is equal to 0, probability of K13 is equal to 0, probability of K23 is equal to 3 by 4. This is our example. Remember, when the plain text is given to you and the key probabilities are given to you, then we have computed for the cipher text, if you remember. Probability of K3 is equal to 1 by 4. Probability of K14 is equal to 0. Probability of K24 is equal to 0. Probability of K34 is equal to 1. So we can compute these probabilities. So that means we can compute HKC. And so HKC turns out to be, this is we are computing directly. So 1 by 8 into 0 plus 7 by 16 into 0.59 plus 1 by 4 into 0.81 plus 3 by 16 into 0. And this turns out to be 0.46 as expected, as here directly computed from the formula, and this we have computed individually. Okay, so that's all. This is the previous example which we computed. I think if you remember, we have given the probabilities of K1, K2, K3, plain text was given, and we computed entropy for the cipher text earlier. Let me see if it is done in this. Yeah, you see these are the values earlier, right? In this example we were talking about. Okay, so once we have done this, so that means we know how to compute the conditional entropy. Okay. Now I'm going to talk about something really interesting known as spurious keys. What are spurious keys, And I will compute a bound on this spurious keys, what is spurious key actually, So basically, suppose we are given a crypto system, P, C, K, E, D. This is our crypto system. Plain text is X1, X2, Xn. Cipher text Y1, Y2, Yn. Okay. Now to determine the key from the ciphertext, so ciphertext is given to you if you have to find the key. Okay, so Oscar may rule out certain keys, but many possible key may remain, only one of which is correct. Okay, so the remaining possible but incorrect keys are called spurious keys. So basically, Oscar may rule out certain keys. From ciphertext, suppose you rule out certain keys, okay, but many possible keys remain, one of which is the correct key. So others incorrect keys, other incorrect keys are known as spurious keys, Let me give you an example here. Suppose ciphertext is WNAJW. I am talking about shift cipher. Okay. So meaningful plain text is river or arena. Okay. And for this, key is F is equal to 5. And for this, key is W is equal to 22. One of them is correct. So one of the key is correct because that will give you the correct answer. Other one is spurious key. Okay, so one of them is correct, other one is spurious key. That's what is known as. So there are. So when you are given a ciphertext, when you are trying to rule out what are the possible keys, you will come up with a set of possible keys that are the possibilities, right? Out of those possible keys, one of them will be correct, rest of them will be incorrect. Okay. So now we can find out, given a crypto system, we can find out a bound on such keys. A bound on such keys. Okay. So I think this is the last result that we are going to do today. And then after that. Now, before discussing spurious keys, I need to talk about one concept known as entropy of a natural language, actually, And I'll show you for English what we can do actually for the English language. So suppose L is a natural language. Okay. So entropy of L, we denote it by HL. Entropy of L, this measures the average information per letter in a meaningful string of plain text. Okay, so our language, natural language could be English, right? English could be another one example. So note that a random string of alphabetic character would have entropy per letter. A random string, if you take of alphabetic character, would have entropy log 2 base 26. 26 total alphabet size, right? Which is equivalent to 4.70. In English, actually, we are talking about. So basically, as a first is the order approximation to HL, or the entropy of the language, right? We take H of P, the plain text, as a random variable. Okay, when L is English, H of P turns out to be approximately 4.19 using Piper table, if you remember. You know, there is a probabilities of English letters, right? So using that, we can compute the entropy of the English language for the plain text, is something around 4.19. Now, successive letters, if you take in a language, are not independent, and correlation among successive letters reduce the entropy. Okay, because in English language, successive letters have some correlation. So for a second order approximation, the entropy of the probability distribution of all diagrams, if you consider, two letters, and divided by 2. Okay, that is the diagram, and divided by, this will be the approximation for second order approximation. In general, okay, so if L is a natural language, I'm just writing a very general result, if P bar n is a random variable, okay, that has its probability distribution that of all n-grams of plain text, okay. So, and we have that probability distribution here, so this is our random variable. In that case, the entropy HL is nothing but limit n tends to infinity h of, because this is random variable, we can compute the entropy divided by n. Just like that, for diagram we divide it by 2, for n-gram we divide it by n, and we can define redundancy of L. RL as 1 minus HL divided by log 2 base P. Okay, so this is our entropy. If L is a natural language, okay, the entropy of the natural language per letter is this. So as I mentioned, for single plain text, then diagram, then trigram, and so on, then we have n-gram, and then the corresponding probability distributions gives you some random variable P bar n. We compute the entropy of that random variable, divide by n, take the limit. So here HL measures the entropy per letter of L. Okay, and a random language would have the entropy log 2 base P. So RL measures the excess characters actually, because this is a kind of redundancy. So for English language, we know that this is for diagrams, this value is 3.90, and HL lies between 1.15. for English language. These are some properties, So that means, using 1.25 as the estimate of HL gives a redundancy of about 0.75 redundancy in the English language. This implies that English language is 75% redundant. This is an observation anyway. Anyway, so that's the basic thing. Let me try to compute the bound now. I think we are ready to compute the bound. This result will not be very difficult to establish, but anyway, let us compute it. So given the probability distribution on K and Pn, one can define induced probability distribution on, because K bar is a random variable. This is the, basically your like diagram, trigram, n-gram, n-gram, random variable corresponding to n-gram, right? So one can get an induced probability distribution on ciphertext of n-gram, the set of n-grams of ciphertext, right? So we have that means we can have, so basically what is this? Pn bar is random variable representing an n-gram of plain text, right? And then we have Cn, random variable of n-gram of ciphertext. Remember, this is the Cn is the n-gram of ciphertext, and this is the corresponding random variable when we are putting bar. Now, given y in Cn, we can define ky, all those key k bar, such that there exists x in plain text Pn, such that probability of x is positive and x bar is positive, and ek of x is equal to y. Okay, so ky is nothing but the set of keys k for which y is the encryption of a meaningful string of plain text of length n. Okay, so in other words, this is a set of possible keys given that y is a ciphertext. Set of possible keys. Y is ciphertext. Okay, given that y is a ciphertext. Now the calculation is easy. If y is the observed string of ciphertext, okay, then number of spurious keys is how much? Total number of keys, because this set is total number of keys, right? So total size will be what? Now out of all possible keys, one of them is correct keys. So the -1, if you remove that one correct key, this is the total number of spurious keys, right? Okay. So now from this, we can compute the average number of spurious keys. over all possible ciphertext strings of length n. Okay, so this will be, I denote it by Sn bar. Okay, summation y belongs to Cn ciphertext probability of y times size of ky minus 1. This is the average for each y, right? As a ciphertext for all possible ciphertext string of length. This is your y. I think I can write it down again. It looks like a problematic thing. Sn is equal to summation y belongs to Cn ciphertext probability of y times ky minus 1. Because this is the total number of spurious keys, right? If y is the observed string. So with respect to overall probabilities, we can take the average, right? So this is the value. Now that means I can take this summation inside and we are left with that Sn bar is equal to summation y belongs to Cn probability of y bar times ky minus summation y in Cn ciphertext probability of y. Okay. Now this quantity is nothing but 1. This quantity is 1, right? So Sn is equal to summation y belongs to Cn probability of y bar times sorry, it's not times ky minus 1. Now I can use certain formulas. We know that what will be this condition entropy? Condition entropy. Now this time is C bar n is a random variable corresponding to n grams, right? Will be h of k plus h of pn. I'm using the formula minus h of cn, right? And h of pn is approximately n times hl. We remember because of the formula, hl is limit of n tends to infinity, hpn divided by n, right? This is nothing but n times 1 minus rl log 2 base what p for large n. Okay. Now h of cn is a random variable, cn bar actually cannot exceed n times log of 2 base quantity of c ciphertext. Okay, so using this result and the above result, we have if cardinality of c is same thing as cardinality of p, then this implies that conditional entropy of these two random variables is at least h of k minus n times rl log 2 base cardinality of p. Okay. Now I can compute another value of the hk of another way. I can compute this directly by definition. Y belongs to Cn probability of y h of a y. This thing is less than or equal to summation y belongs to Cn probability of y times log 2 base ky for all keys. Now we apply fx equal to Jensen equality on log 2 base x using Jensen's inequality, right? Thing is less than or equal to log 2 base summation y belongs to Cn, probability of y, okay, and that means nothing but by definition this is log of 2 base Sn plus 1, because initially we have computed the value of Sn, okay. So this implies that we have two values of HKCN. So combining these two values, so one of them is, this implies that we have HKCN is at most log 2 base Sn plus 1, right? Combining the two, we have log 2 base Sn plus 1 is at least h of k minus n times RL log 2 base p. So this is the bound. In other words, actually, HK could be maximum when keys are chosen equiprobably. In that case, we have the following result, which is the final result. So suppose P, C, K, E, and D is a crypto system where cardinality of C is same thing as cardinality of P, and keys are chosen equiprobably. In that case, actually HK is maximum. Okay, HK is maximum. So basically, we have, if RL denotes a redundancy, RL denotes a redundancy of the language, then given a string of ciphertext of length n, given a string of ciphertext of length n, n is sufficiently large, okay, the expected number of spurious keys Sn bar is at least cardinality of k divided by nRL minus 1, okay, because hk is maximum, so we've taken the maximum value and then simplifying the inequality we'll arrive at this. Okay, final concept that is there now I would like to tell you is known as unicity distance. So unity distance of a crypto system is a value of n, we denote it by n naught, okay, at which the expected number of spurious keys becomes 0. So from the key, from actually this bound, we arrive at this, okay. That is the average amount of ciphertext required for an opponent to be able to uniquely compute the key given the enough computational time. So we can actually, if we set Sn is equal to 0 and solve for n, we get an expression for this. N naught is nothing but unicity distance is log 2 base mod of k divided by RL times log 2 base this quantity. So this is the formula for unicity distance. Okay. Now for a given crypto system, say for example substitution cipher, I can compute this value, because we know the size of k and size of p, and the redundancy you can compute, right? So for substitution cipher, size of p is 26 and size of k is equal to factorial 26, number of keys, right? And if we take redundancy to be 0.75, we just saw that earlier. So n naught turns out to be 88.4 divided by 0.75 into 4.7, which is roughly equivalent to 25. This implies that given a ciphertext, ciphertext string of length at least 25, usually a unique description is possible. And that's all. So I think that's all for the basics. We are able to cover the basics. Now I think I should mention some topics for your projects, so that you know what are the topics you can pick up. Okay, you can pick up blockchain and cryptocurrency. This is very popular one. So in the blockchain cryptocurrency, see, blockchain is a very basic idea applied to so many places. So it could be IoT, it could be it could be your medical area, it could be all sorts of life. Whenever there is some sort of notion of money is involved, actually you can apply blockchain, or asset distribution actually. Okay, so plenty of opportunities are there in blockchain cryptocurrency. Then we have, this is very hot area obviously. Then we have basically homomorphic encryption. Then we have actually NTRU, CTRU. Okay, tools for cyber security. You can develop a lot of tools, that you can pick up for cyber security. Okay, and post quantum crypto system. So out of this, I think two popular ones are lattice based cryptography. Another one is code based cryptography, right? Then we can also do directly quantum cryptography based on quantum computers. Then we can do DNA cryptography. Okay, so post quantum, I mentioned only two popular ones. There are plenty of ones. Actually, you can look at National Institute of Standards in US, and you will see a lot of candidates. But these are the two popular ones, actually. So, any question about these projects? You can ask me.
Sir, the projects are individual or in a group?
In a group, cloud cryptography. It's in a group. Okay. So
And the groups will be formed by you?
No,
or
by
we can choose
you.
our group.
I don't want to form the group. It is up to you. You can, you must be comfortable with some people.
Okay, sir. Thank you.
Hmm.
Sir,
Yeah.
what should be the group size?
I think since there are about 150 people in the class, I would say 3 to 5 will be good enough. 3 to 5,
Okay, sir.
right?
Thank you.
Yeah. So I think you can start exploring these ideas. And I will give you more list again. So this is just some sample list. Blockchain, I'm sure. I think many of you like blockchain because plenty of things are there possible. Some people are working with me on that. So we could be developing tools and so on, or maybe a protocol or some sort of paper writing is possible in if you are continuing in the summer. Otherwise, for the course you can do something meaningful. We will be, as I mentioned, we will be inviting some experts to have more and more use cases of the industry so that you can get first-hand experience of the industrial projects. Okay. So I think we are not keeping any final exams. There is only one exam, and then there is a project finally. Okay. So that's the idea right now. So I think all the basic is done right now. Now in the next class we will start working towards DES and AES, the two popular. DES, as you know, is the first system. These are the part of symmetric cryptography. Okay, so there we will be using some sort of permutations, substitutions, and those kind of things, which are pretty useful in developing those algorithms. I show you how those algorithms are working, and and then so you have some basic understanding. Okay. So basically, we are talking about block ciphers, and then briefly we'll discuss about the stream ciphers as well. By the way, there is another important area is Boolean functions and cryptography. Okay, uh, one popular one is known as bent functions. Bent functions. So I think you can see what are these things. Okay. There is another area known as visual cryptography. These are some general areas. Problems could be very specific in that domain. Okay. So look at some of these interesting things and let me know what you want to do. As you know, this is security and cryptography is really very very fundamental thing to your life. Everywhere you will find applications. Basically, another one is, I can mention 12th is your IoT, Internet of Applications and Cryptography. Okay. Internet of Applications and Cryptography. So that's another area. Any more question? Okay, so I think if there are no more questions, thank you very much, and see you in the next class when we will talk about other things. Let me